So 2-point charges are separated by a distance of 10 centimeters. The one on the left has a charge of negative 25 microcoulombs, and the one on the right has a charge of positive 50 microcoulombs. And they're 10 centimeters apart, or 0.1 meters. And we want to find the electric field 2 centimeters to the right of the negative charge. So 2 centimeters to the right will put you about right here. So I'm going to draw an X at that point, signifying that that's where we want to find the electric field. So there's two components to the electric field, because there's an electric field due to this charge, and there's going to be an electric field due to this charge. So first thing we can talk about is what is the direction of the electric field. Well, we know that the electric field is a vector, so it points toward negative charges and away from positive charges. So from this negative charge, the electric field at that point is going to point toward it. So the electric field would be directed to the left. So I'll put an arrow on here representing that's the electric field due to charge 1. So I'm going to call that E1. Now we have this charge on the right, which has an electric field. The electric field is directed away from positive charges. So that means at every point in space, the electric field will be going away from that charge. So at this point right here, where we're looking for the electric field, directed away from it would be in the exact same direction as the E1. So I can draw a second arrow on here, right over top of that one, and call it E2. So those are going to be based on the fact that the charge on the left I'm calling Q1, and the charge on the right I'm calling Q2. So we want to solve for E1 and E2, and then because they're both in the same direction, we can just add them together and say that the total direction of the field is to the left. If they were in opposite directions, if E1 went one way and E2 went the other way, then we'd have to subtract them, and whichever one was bigger, that would be the direction of the field. But in this case, it's easy since they're in the same direction. So we'll figure out that E1 is equal to, the formula for electric field due to a point charge is K Q1 over R1 squared, where in this case the Q is just the magnitude of the charge. Again, you're not going to put the negative sign, just focus on the magnitude of the charge. You always do that for when you're dealing with vectors, which are force or electric field. And then the R1, that's the distance from that charge to where we want the electric field, right here, which is 2 centimeters or 0.02 meters. So if you plug in 9 times 10 to the 9th times Q1, which is 25 times 10 to the negative 6, divided by 0.02 squared, you'll get an electric field due to charge 1 of 5.625 times 10 to the 8, and remember electric field is measured in units of newtons per coulomb. Let's do the same thing for the electric field due to the positive charge. So that's going to be K Q2 over R2 squared. So plug in the numbers, 9 times 10 to the 9th times 50 microcoulombs, that's 50 E negative 6, divided by the distance from that charge to where you want to find the electric field. If the whole distance is 10 centimeters, and this distance is 2 centimeters, that means left over here is going to be 8 centimeters, or 0.08 meters, and that's squared. And when you plug in those numbers, you get an answer of 7.03 times 10 to the 7th power newtons per coulomb, which means the total electric field, and if you want, you can put an arrow for both these indicating that the field was to the left. The total electric field, which I'm just going to call E, is the vector sum of E1 plus E2, which since they're in the same direction, when you add those together, you're just going to get 6.33 times 10 to the 8th newtons per coulomb. And that's the magnitude. You also want to indicate the direction, which in this case you can just say the direction is to the left, or you can say west, or you can say 180 degrees from the x-axis, however you want to say it. For part B, since all that was part A, if a proton were placed at rest at that point and then released, what would be the magnitude and direction of its acceleration? Well, since a proton is positive, positive charges always move in the direction of the electric field, so the direction is easy, it's to the left. If it were an electron or some other negative charges move in the opposite direction to the electric field, so that would go to the right. But the proton is going to move to the left. So now we just got to figure out what's the magnitude. We know that when a charge is placed in an electric field, there's a force on that charge equal to Q times whatever the electric field is. And since force is equal to mass times acceleration, we can actually write this as ma is equal to QE and just solve for the acceleration. So A is equal to QE divided by m. The charge of a proton is 1.6 times 10 to the negative 19 times the electric field, which we just figured out, is 6.33 times 10 to the 8th, divided by the mass of a proton, which you can look that up in the chart, is 1.67 e to the negative 27, and that gives you an answer of 6.06 times 10 to the 16th, and this was acceleration we're looking for, which is meters per second squared. And we already said earlier that because it's a positive charge, it moves in the direction of the electric field, which is to the left. And finally, part C, you want to figure out, is there anywhere in the vicinity of the two charges where the electric field is 0? We could figure out an exact location, but I'm not going to now. But if you want to, go ahead. All I'm going to ask you to do is figure out where, roughly, it's going to be equal to 0. So the first thing is, we know that between the two charges, the electric field due to the negative charge is to the left, and the electric field due to the positive charge is also to the left. So nowhere between the two charges is going to equal to 0, because the two electric fields are always in the same direction. They're never going to cancel out. What if we look over on the right side, like over in this area? You can see that if we pretend this charge isn't even here, so ignore the positive charge, just look at this negative charge. From this negative charge, the electric field over in this area will be pointing toward it, because electric fields go into the negative charge. So we could say that E1 would be this way, and the electric field due to the positive charge, where electric fields come out of it, so it goes away from it. So we can say that E2 is that way. But is it possible that those two things can cancel out? We'll come back to that question in a second. Let's also look in the area over to the left of the negative charge. To the left of the negative charge, well, the electric field from a negative charge points toward it. So we could say that over here, the E1 would be pointing this way. And then if we pretended this charge doesn't exist, like it was gone, the electric field due to this charge is a positive charge, so the electric field is going to go away from it. So we could say that the E2 is that way, which also seems like they could cancel out. So now let's answer the question, is it possible that they can actually cancel out? Well, the equation for electric field is kq over r squared. So if we look at this one over here, the closer charge has a bigger value of q. So in this case, the E2 is going to have a bigger value of q, because it's a bigger charge, and at the same time a lower value of r. So E2 has to be bigger than E1. There's no way to make this equation such that E2 is equal to E1. So this side won't work. It's impossible to have 0 electric field over there. But on this side, since the bigger charge is further away, the Q2 is bigger, but the distance of that charge is also bigger. Since both of these are bigger, it's possible that E2 could actually equal to E1. So at one point somewhere over here, these two electric fields could actually equal each other, which means they would cancel out, so you would have an electric field equal to 0. So all you have to say for part C is that to the left of Q1, the electric field could be 0. There is a way to figure out the exact distance if you really want to go through and set up the equations. set the two electric fields equal to each other, but I'm not expecting you to do that right now. Just know that the electric field can be 0 to the left of Q1.